In this work, we present learning predictive models for ergonomic control of prosthetic devices. One of the open challenges in powered prosthetics is the creation of responsive but safe control policies. Since amputees are especially susceptible to musculoskeletal conditions such as osteoarthritis, new approaches are needed which are responsive to changes in gait or perturbations while remaining mindful of the biomechanical ramifications of control actions. We proposed a data-driven method to human-machine symbiosis called Model-Predictive Interaction Primitives, in which assistive devices use a model-based approach to predict future actions as well as hidden biomechanical variables from user input. We can then adapt the actions to elicit specific biomechanical responses from the paired subject, such as a reduction in knee force, moment, or impulse. Pairing machine learning with classical control methods in this way creates a collaborative process to generate healthy and ergonomic interactions within task constraints. The probabilistic model we utilize is called interaction primitives, which is a fast and effective method for human-robot interactions. Our method takes collected sensor data from human demonstrations and, using a state-of-the-art biomechanics simulator, adds computed biomechanical values such as joint angles, forces, and moments. We then learn a Bayesian framework, which generates predictions of the state and action of a subject given the requisite observable sensor values. Once trained, an interaction primitive anticipates the future states of the human user from observed sensors and infers latent unobserved variables such as the internal forces and device control values without the necessity of further biomechanical simulations, a necessity for the use of real-time model predictive control later on. To begin learning, we first combine the observed sensor vectors with augmented biomechanics. Probabilistically, the objective of interaction primitives is to infer the future state of the full observation vector given a set of observations. We simplify the process by projecting the full state trajectory in time into a lower dimensional space using von Mises basis functions to account for the periodic nature of the behavior. We then rewrite our goal equation to incorporate the basis function approximation and can see that it can easily be solved recursively with a Bayesian filter. In this work, we utilize a Kalman filter to achieve human action prediction, latent variable prediction, and robot action generation. In the model predictive control step, we take the predicted latent variables and, using the probabilistic model, optimize continuous controls which minimize or maximize the latent biomechanical trajectories. We once again benefit from our transition into the basis space as we can pre-compute the integration, making the MPC process much faster. Utilizing modern multi-objective MPC solvers allows us to add additional objectives such as limiting changes in the control trajectory. To demonstrate our method, we collected training data where the subject was instructed to jump vertically and then land in two ways. First, as soft as possible, and second, with the largest impact they are comfortable with. The data was augmented with joint reaction forces calculated from force sensors and human biomechanics model via inverse dynamics. As you can see, the subject naturally chose to either land softly on their toes or hard on their heels. The learned probabilistic model with our MPC extension then controls a powered robotic prosthesis with a parallel spring mechanism, namely the spring-active ruggedized Odyssey ankle. Due to the nature of the jump, it is impossible for our interaction primitive model to accurately differentiate between the two modalities, soft and hard landing, since both exist as equally likely possibilities. We should therefore expect the probabilistic model to perform some average control trajectory. However, due to ergonomic considerations and the long-term health benefits from reducing joint impacts, it would be beneficial to select the type of impact desired. Our model predictive control extension does just that, and shows successful optimization of the ankle angle control to either reduce the impact force on the knee joint or to increase it. Note that in a side-by-side comparison of knee force minimization and maximization, the ankle angle begins to move while still in the air to adjust for the desired angle during landing. When the foot touches down, the force minimization control has already extended the toe to help catch the weight in a soft and controlled manner, whereas the force maximization control has pulled the toe up to hit with full force, further illustrating an optimization of the current trajectory given future state predictions. Thank you.